All right, this is the second lesson of topic 2. For this lesson, you're going to need 4 sheets of patty paper, 2 for the lesson and then 2 more for the homework. You're going to need a pencil and you're going to need a straight edge, and I would recommend using your compass because we're going to be doing a couple of measurements as well, and your compass has a ruler along the side. So today at the end of the lesson, I want you to be able to understand and apply the geometric definition of both translations and reflections. And then understand that a translation is a composition of 2 transformations, and we're going to know exactly what 2 transformations those are. So on your notes, I want you to go ahead and attempt to answer question 1 on your own. You're always going to be starting with triangle 5. So triangle 5 is your pre-image, and these are possible images of triangle 5. So you're trying to find which one of the triangles is a reflection across the x-axis from triangle 5. And then again, which one of these is a translation down 6 and left 8 units from triangle 5. So you're always starting at triangle 5. If none of them are one of these transformations, then just write no triangle. So you can start back this video as soon as you are finished with that. Okay, so let's see how you did. So if I'm looking at reflecting across the x-axis, this horizontal axis is the x. And so if I reflect, which remember the slang word for that is a flip, but we're always going to use proper mathematical terms, so it's reflection. If we reflect at triangle 5 over the x-axis, then every point on triangle 5 is going to be the same distance from the x-axis, but on the opposite side. So this point would reflect to this point. This point would reflect here, and this point would reflect here. So triangle 4 is the correct answer for that first part. Again, we're going back to triangle 5. We're going to see which one is a translation down 6 units and left 8. So you could start at this vertex of triangle 5, count down 6, and to the left 8. And we end up to that vertex right there. And you could do the same with this one, down 6, left 8, and this one, down 6, left 8. And you will find that you do indeed get to triangle 3 for the second one. Now, the third one is a rotation 180 degrees around the origin. So if I'm taking triangle 5 and it doesn't tell me which direction to go, remember the natural progression is going to be counterclockwise around a coordinate grid. So you might think it would be clockwise, but it's actually the same way that we named the quadrants of the coordinate grid. Remember, this is your first quadrant. This is your second quadrant. I'm so sorry. How about I make that big for you guys? This is my second quadrant. This is the third, and this is the fourth. So the natural progression around a coordinate plane is counterclockwise. So 180 degrees doesn't really matter because if I went 180 degrees counterclockwise, it's going to have the same effect as 180 degrees clockwise because it's half of a turn. But 90 degrees, it would definitely matter which direction you go. So I know triangle 5 is going to end up in the third quadrant when I go 180 degrees, but it doesn't just slide there. It's turning as it is going. And so we can think about this point right here. 180 degree angle is a straight line. So with the origin and the new point for that point right there, so that's my pre-image, my image would have to be in a line with the origin on this other side. And you can see we don't have a point in a straight line from that vertex. So we do not actually have a triangle that is a 180 degree rotation of triangle 5 around the origin. So again, this point, the origin, and a point would have to be in a line. We have one there, but when we look here, we don't have one in a line with that. And here we definitely don't. So this is not triangle 3. Okay, remember that this is going to be turning as it's rotating. So it won't look exactly in the same orientation as what we call that as triangle 5. It'll be facing a different direction. All right, in the final one, starting back at triangle 5, we're reflecting across the y-axis. So the vertical axis is the y. Every point's going to stay the same distance from y, but on the opposite side. So this point goes to this point to this one, and this one to that one. So this correct answer is triangle 2. So hopefully you got at least 3 of those correct. The third one might have been a little tricky for you. All right, in order to answer questions 2 through 4, we're going to have to do a paper folding with patty paper. So go ahead and grab your first sheet of patty paper for this exercise. Let me get a blank sheet of paper so we can have a clear surface here. Okay, so we're going to start off by just drawing a line, and it doesn't have to be going straight across your paper horizontally. I'm going to kind of do it at an angle here, and we're going to name this line M. So remember, if we're naming it, we're going to use a lowercase, and sorry, my light went off in my room. I'll pause. If I'm naming a line with just one letter, it's going to be a lowercase scripted letter. So I'm going to put a lowercase scripted M. So this is now called line M. So remember, that's not a point on the line because points are always capital letters. This is just simply the name of the line. We're going to put a point P. I'm not going to put it like extremely far away from the line, but I'm going to put it above the line, and I'm going to name that point P. And we are going to fold the reflection of point P. And to do that, all I'm going to do is make my fold go right along that line M. So if you'll fold your patty paper right across line M and crease that like so, I'll open it so you can see my crease goes right along line M. And I'm going to keep it creased, and I'm going to trace that point P. I can see through the patty paper, so that allows me to trace that point. So now when I open up my paper, I can see that point down here that I traced. And so this point is the reflection of this point along that line. Now this is called the image of point P. And so to show that, we also use a capital letter P, but we put a little apostrophe beside it, and that's a prime symbol. So we call that P prime, which just means the image of point P. So again, this is the reflection of that point. So we're going to connect those 2 points, point P and P prime, with our straight edge. So we just made segment P prime. And I'm going to label where that segment intersected line M with a point M. So now it's a capital letter M. And I'm going to put another point along line M, and I'm going to name that point point A. So again, that's capital letters. So points are always capital letters, but a name of a line can be a lower case scripted letter. Okay, so we're going to answer some questions on our notes based on our patty paper exploration. So you can see I'll just keep this up here and we'll just answer the questions here. It says on number 2, if I can get situated here, that P prime is a reflection of P across line M. What must be true about segment PM and segment P prime M? So it's wanting to know, and I can just use this picture here as well. It's wanting to know what has to be true about this segment, P to M, and this segment, M to P prime. Well, since it's a reflection, and I can verify this with my fold, you can tell those 2 segments are right on top of each other, which means they have to be congruent to each other. So we can say that segment PM is congruent, which remember is the equal sign with a little squiggly above it, segment P prime M. They're congruent to each other. They have exactly the same length. Number 3 says, what appears to be true about angle PMA, so we're talking about this angle right here, and angle P prime MA, which is this angle right here. Now, they are also congruent, and I can verify that with my fold. Those 2 angles are right on top of each other. And since they make a line together, that means they have to add up to be 180 degrees. So if they're congruent and add to 180, that means each one of them has to be 90 degrees, or in other words, a right angle. So angle PMA and angle P prime MA appear to be right angles. All right, so let's look at the next question, number 4. What does the conclusion you reached in questions 2 and 3 tell you about line M and segment P prime P? So line M, we just said, is making these right angles here. And we said in number 2 that PM and P prime M are congruent to each other. So if we're creating a perpendicular relationship and congruency at the same time, then that means line M has to be a perpendicular bisector of this segment P prime. So let's write that in words. Line M is and remember the sign for perpendicular is an upside down T, is a perpendicular bisector of segment P prime P. So don't forget those symbols. We're not talking about the measure, we're talking about the segment itself. And that's a lower hand scripted M for its name. So now let's look at filling in number 5 of our notes. So here is the definition of a reflection, and you can fill in the lines based on this statement right here. Point P prime is the reflection, that's your first blank, reflection, across line M of point P if line M is the perpendicular bisector of segment P prime P. So is the perpendicular bisector. That goes in your second and third blanks. So on your notes, you should have point P prime is the reflection across line M of point P if line M is the perpendicular bisector of segment P prime P. All right, so let's look at question 6 on our notes using that information. So it gives me 2 different expressions, one for P to M and one for P prime to M. Now remember, we just said those were congruent links, those were congruent segments, which means their measures are equal. So all we have to do is set these 2 expressions equal to each other. So 3x minus 5 equals x squared minus 5. So remember, with quadratics, we want to get everything on one side set equal to 0. So the 3x and the negative 5 are going to move over to keep x squared positive, and don't forget to change their signs. So the x squared is first, the 3x comes over and becomes negative 3x, the negative 5 comes over and becomes positive 5, but when it combines with negative 5, becomes 0. So I don't need to write plus 0. I can just leave it just like this, x squared minus 3x. Now to factor this, I'm not going to get 2 binomial factors because I don't have a trinomial here. I only have 2 terms. So to factor this, I'm just going to factor out what they have in common. So both of those terms have an x in common. That's what's going to go on the outside that I'm factoring. So x times what gives me x squared? Well, this has to be an x here. And x times what gives me negative 3x? This has to be a negative 3. So x times x is x squared. X times negative 3 is negative 3x. I'm still using the 0 product property, which says if these 2 things are multiplying to get 0, then at least one of them has to be 0. So either the x is 0 or the x minus 3 is 0. And if the x minus 3 is 0, I would add 3 to both sides to get x equals 3. Now, not both of these make sense geometrically, even though they are correct solutions algebraically. Because if I put 0 in for x, in for PM, 3 times 0 is 0, minus 5 is negative 5. Doesn't make sense for that distance from P to M to be a negative distance. So this is not a valid answer geometrically. Now, if I put the 3 in, and I put that in for x here, 3 times 3 is 9, minus 5 is 4. And here, 3 squared is 9, minus 5 is 4. So both PM and P prime M are both 4, and we're given units of millimeters. Now the question was, find P prime. So P prime is that whole distance across. So all we would have to do is add 4 millimeters plus 4 millimeters. So my answer is P prime is equal to 8 millimeters. All right, you'll need another sheet of patty paper for the next video.